Mega Mechatronics.
Welcome to the Mechatronics Bootcamp series for mechanical engineering. Today we're going to be talking about materials, stress and strain. Throughout this series we're going to cover topics on stress and strain, ductility, corrosion, hardening and heat treatments, failure analysis, surface finish, and thermodynamics. And we're going to be covering stress and strain today. So let's talk about what stress is. The units of stress are expressed as a pressure, like the pressure in your tire, atmospheric pressure. So that's a force per unit of area. And the units are, here in the States, pounds per square inch, or KSI, which is PSI divided by 1,000. Or in the metric system, we have newtons per square meter, known as pascals, megapascals, and gigapascals. So let's say we have this material here, this column, and we apply 10 pounds to it. So let's figure out the stress. So stress is the load of 10 pounds, we know that, divided by the area. We're going to have to calculate the area. So here's some of the formulas. This is going to be a square rectangle, same thing, length times width. You see the triangle and the circle there. So here let's say it's a 1/2 inch by 1/2 inch. So 0.5 times 0.5 is going to give us 0.25. So throw that in our formula, 10 pounds divided by 0.25. That's the area. And that's going to give us 40 psi of stress within that column. And that's why something like a thumbtack can press into a wall so easily, because that point is so tiny, and that will affect the formula here and increase the psi to a very high number. And now we're moving on to strain. Strain doesn't have any units. It's unitless because it is a ratio of two lengths. So that's going to equal the change in length, delta change, divided by the initial length. And this applies to anything you want to calculate the percent change of. You take that change divided by the initial. And it also equals stress divided by the modulus of elasticity of that material. So all materials are classified with some sort of modulus, or Young's modulus, same thing. And you can see how we flip that formula around, because Young's modulus is stress divided by strain. So let's take our sample column here, and let's say we pull on this thing and we stretch it out a little bit. So we started with 4 inches and we stretched it 0.050, 50 thousandths of an inch. Not very much. So again, we're going to take that change. We're not taking the total length of that. So 50 thou divided by 4 inches. That's going to give us a strain of 0.0125 or 1.25%. So we change that length by 1.25%. And that's strain. So how are materials stressed? So here are the 3 basic ways a material will be stressed. So compression, where you're trying to smash that column together like you're building a snowball, compressing it. Tensile, we're pulling on it really hard, like when you pull on a rope, it's under tension. And then shearing, so you can see how those arrows are slightly offset, and that's the shear. So if the arrows were in line, that would be compression. And so let's say we have a beam, and we bend this beam. So this is experiencing more than one stress, one type of stress. It's going to be under tension up top and under compression at the bottom. You can see an example here. The piece of paper, see, it's going to tear at the top because it's under tension. That's typically how stuff fails under a bending moment like this. And you see how the bottom side folds up because it's under compression. So how do we measure stress and strain? The most popular way is a tensile test. So we have this test specimen, it's all standardized size, and we put it in between 2 jaws, put a little gauge on there to measure the change in distance, and you pull it apart. So here's an example of a real life one with some self-locking jaws there, and you can see that gauge. So the specimens, typically the flat ones, are for polymer materials, synthetics. And then for the metals, we have a little bit larger piece there. I'll show you in this video. I have one on hand. That's a piece of aluminum bar stock, and you machine it down and to a standard diameter. So that's a 1/2 inch, and we can use that to compare against other 1/2 inch samples. And how you machine the jaws depends on the machine you're using. Some use threaded ends, so that's quite important so you don't slip in the jaws there. So let's see how what we're measuring relates to the infamous stress and strain curve, which is really the point of this video. So we're going to take that stress because we're going to calculate the area of that specimen. So that specimen is rectangular, we would find the area that way, or the round one, we use the area of a circle. So we know the force because we're measuring it, and then we input the unit area. We're going to throw that over there. And for the distance measurement, again, the computer would handle these calculations. The change in length divided by the initial length between those measuring little measuring jaws there. And we're going to plot that on the strain curve at the bottom. So here's that stress strain curve again. Looking at the bottom, you can see how the strain lines up there. So going across the top, that's about 400 megapascals of stress, and we're getting a small amount of strain. We're moving across to about 700 megapascals of stress, and you can see we have significantly more strain happening, more change in length. And then some materials will experience this where you require that same maybe 650 MPa, and we're way over on the strain, and then until it fractures, and that's our breaking strength right there. So there's some important attributes to the stress strain curve that we need to understand. First, we have the elastic region, and this is essentially the springiness of the material, you can say. The slope is related to the stiffness, so the steeper the slope, the stiffer it is. And you can see I have a piece of steel wire here. I'm bending it, and it doesn't deform. So when I put it down by the ruler, it is still straight. So we stayed in the elastic region, and that's elastic like a rubber band, because you can stretch a rubber band and it returns to its shape. And then up here is the yield point. So we're beginning our little hockey stick here, and that's when the material yields. It says, hey, I can't handle this, and it starts to deform permanently in the non-elastic region. So you can see I have this steel rod again, and I will apply a stress above the yield point, and then it obviously permanently deforms it. And then at the end of this curve is the failure point. So we have the elastic region, which is very important, where it returns to its original shape, and then we have the plastic deformation past the yield point. This is where permanent deformation occurs. Looking at this graph to compare some different materials, we see A is very strong, B is very brittle. You see there's it doesn't even yield, it just breaks. And then C is not quite as stiff, but it is quite ductile. You see how far we had to strain it before it broke, so it's stretching out like a piece of gum. And then D is not very stiff, low strength, and kind of ductile. So ultimate strength, this is something that you need to know. And when comparing materials and looking up material properties, this will be listed along with yield strength. So the ultimate strength is going to be the maximum stress that it experienced during this test. So you can see the different maximums here. So it's not just the breaking point. with B, the yield and the ultimate strength are the same, but you can see how C continued after the ultimate strength, same with A. And this is what's so good about stress strain curves. We can visually compare materials very easily here because we're using stress, which is standardized load per area, and then strain is a ratio. So we can take data from some other tests and actually overlay it, even if they tested it in a little bit different way. And then various alloys, you can see the steels are up top, stainless, and then we're going down to aluminum, mild steel, and then magnesium right at the bottom there. Elongation, this is important, and I'll show you how that's measured. So before the specimen is pulled, we're going to take a measurement of some known marks. So maybe we'll take a Sharpie. Sometimes you can put a dimple in there or something. And then after the test, you can see how it is a little longer because it necked down and pulled apart, and then it failed. So we're going to actually put those pieces back together after it broke, and then measure that change. So it is actually strain. So if you look at the stress strain curve and at the breaking point, and then you go down to the strain, you're going to see the elongation percentage there. So percent of elongation, that's another proxy to compare materials. And there's still other tests, and I'm not covering every single material test here, just covering the most popular ones. Here's torsional testing. So we take the torque and then calculate the stress and then the angle of change, and that will be part of the strain calculation. And shear testing up here. We can test the shear directly. So we have our initial condition, and then you see after the test, or during the test while it's being strained, it sort of cuts across there. Like you're using scissors, you're using shears to cut something. So here's a working example of a bolt under a shear stress. That's something you'd test for fasteners. You'd want the shear strength when you're looking up a fastener that will be under shear load. And that concludes our stress and strain tutorial. Thank you for watching.